Taste your fingertips, the feeling of your skin, love, give me love, 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 love. Now we start talking about it. You got a perfect one, so put it on me. Swear it won't take you long if you love me right. We fight for life on and on.
Called conservative, or sometimes it's also called the gradient vector field. They commonly use conservative to refer to these, but I think that gradient is more explanatory of what's actually going on. So I usually, it's interchangeable basically. So what that means is that some vector field F, let's say, F, again, conservative means that F is a gradient, basically, is a gradient of a differentiable function, I'll abbreviate here, differentiable function. And they traditionally use v of x comma y comma z. Or you could have just of x and y, but it's usually in 3 dimensions. So anyways, what this means, I guess more mathematically, without words, is that f equals the gradient of v. Alright, the upside down triangle means gradient. And then gradient, you probably learned this in 32a. We dealt with this a little bit. So this is basically the vector formed by the partial derivatives of the function v. Okay, so it would be partial v partial x, partial v partial y, and partial v partial z. Okay, so this equation right here, that's basically all of what a conservative vector field is. So the terminology here, so this is called the conservative vector field. This v here, so v of x, y, z, that is called your scalar, because that's not a vector, it doesn't have the little arrow on top, but it is a scalar potential function. That's the terminology for that. Potential function, okay, for f. Okay? Alright, so I'll go into more detail on the next slide. So what we have is, remember before, we're just going to stick with 3 components here. So in the beginning, I introduced the vector field in 3 components as looking something like this, right? With 3 components, f sub 1, f sub 2, and f sub 3, each depending on some combination of x, y, and z, right? So something like this, okay? So that's the definition of a vector field, basically. And then, if we take into consideration the conservative vector field, which is the gradient of v, this part, separately, would look like the partials again, right? So partial v partial x, partial v partial y, and partial v partial z. Okay? So, as you can see here, so I'll say when vector field F is conservative, the following happens. Then the first components are going to be equal, the second components are going to be equal, and the third components are going to be equal. Right? So f sub 1 of x, y, and z is going to equal the partial v partial x, where v is your potential function. It's a scalar, not a vector field itself. And then f sub 2, that function is going to be the partial v partial y. And lastly, we have f sub 3 equal to partial v partial z. Okay? So here, that was kind of, you can kind of tell, just connect the dots here. But now something important is going to go on. So we're considering the condition when f is conservative, right? So that's when it is the gradient of some scalar function. So furthermore, we're going to go a step further. And what I'm going to do now is take another derivative. So let's compare these two first. So let's say I take the partial derivative with respect to y of f sub 1. Okay? So what that's going to mean is that this is the partial of y of the partial of v partial x, right? So if I do partial derivative of y on both sides, this is what I get, okay? And then what this is, just ignore this error right now, but I'm just continuing here. So what that turns into is the second partial of v first with respect to x and then with respect to y. It goes kind of backwards here. But anyways, so this is what we end up with when we take the partial of y of all of this. And now I'm going to take the partial of x with respect to, or take the partial of f sub 2 with respect to x. So that would be partial of x of f sub 2. And then that means I have to do the same thing on the other side, right? So partial v, partial y. Okay, I'm just continuing here, following through with the math. And then we have something that looks like that, right? Second derivative, okay, and we just took the steps here and took it a step further by taking the partials with respect to different variables. But as you can see, this here and this here, if you recall from Math 32A, the course before this, these are technically called cross partials. So by Clairaut's theorem, if you remember that guy, okay, hold on, I'm going to try to spell this right. So that's an I, Clairaut's theorem says that the second derivatives, or the cross partials have to be equal. So basically, these things are equal, so that I'll just say that these are, or I'll make it assertive, these must be equal, okay, if you have the same potential function. So what this means is that, I'll start on the next slide. So this leads us to the cross partials property of conservative vector fields, of conservative vector fields. Okay, so what this is, I'm just going to write a series of conditions basically. So if the vector field f, which is composed of an f1, an f2, and an f3, which each depend on x, y, and z in some way, if this is conservative, then we have our big then we're going to have that the partial of the first component here, with respect to y, is equal to the partial of f2 with respect to x. Okay, and then we're going to have, so that's comparing the first two, right? Now we'll compare the last two. So if we take the partial of f2 with respect to z, and that should be equal to the partial of f sub 3 with respect to y. So here's a comma in between. I'll just draw a line. So these are three different conditions that must be satisfied for the vector field f to be conservative. And then the last one is comparing the outside one. So partial of f sub 1 with respect to z must equal the partial of f3 partial x. Okay? So these must be fulfilled. This is a condition that must be satisfied in order for the vector field to be considered conservative. Alright? So let's do an example of this. So we're going to say, example, is f conservative? Okay? And we're given f equals y, z squared, and x. Alright? So this y is our f1, this is our f2, and this is our f3. Alright, so let's check. Does partial of f1 partial y equal partial of f2 partial x? Is this true? So let's do the first one. So we have partial with respect to y of f1, which is y. So that's going to just be equal to 1, right? And now let's do this one. So that was that. And now let's do the partial of f2 with respect to x. So that would be partial with respect to x of z squared. Sorry if you hear a dog in the background. My neighbors have dogs. Anyway, so continuing here, if you differentiate with respect to x, there are no x's here. And this is considered a constant, so then we just get 0, right? So as you can see, 1 is not equal to 0, and I don't think it ever will be. So that is not true. So this vector field is not, emphasis on the not, conservative. And if you want to get fancy with it, you can also say because cross partials condition is not satisfied. Okay? And also satisfied. Alright, so on some problems, they'll have you check, like, is this conservative or not? Is this vector field conservative or not? And you'll go through, like, the first one and check the cross partials, and they will be equal. But you can't stop there. You have to, if it has 3 components, you have to do all 3 pairs. You have to check all 3 pairs of the cross partials, and every single one of them must be equal. Okay, so if 2 of them are equal and then 1 is not, that means it's not conservative. Okay, and then in the 2-dimensional case, if you have like a vector field of 2 components, so like y squared and x squared, or something like that, then you have to do the cross partials 2 times. Okay, because you don't have a 3rd component to compare it with. So, okay, all right. Now on to the last topic for this video. So now we have something called, just building off of what we've been doing so far. So this is called uniqueness of potential functions. Potential functions. And these potential functions that I'm referring to are like the v, right? So like v of x, y, z, right? So we have, here I'll draw a little line. So if f is conservative, on an open, and I'll explain what these mean. Open connected domain, then any 2 potential functions of f, I'm almost done, differ by a constant. Okay? And constant meaning just a non-variable thing. So like a number. Okay, so what this translates to is that when you're on an open connected domain, so that just means pretty much everywhere, and there's no holes or places where your vector field f is not defined, then any 2 potential functions, so the v's of them, of f, differ by a constant. So let's say you have a vector field, right? Well, I'll put it like this. So a vector field of x and y equals, let's say, y comma x. Okay? And so this is your f sub 1, and this is your f sub 2. And basically what we have is that if you solve and go backwards, kind of, the gradient of v, like that, is going to equal, wait, hold on here. That's not correct. This is the gradient of v, so this equals gradient of v, okay? So if you go backwards, and we'll go over this in, I think, in two more sections, in a future section. But anyways, so the point here is that at v of x comma y could equal xy, right? Plus any number c. So basically when you do this, you could check too. So let's take the partial of v with respect to x. And that would be, so if we differentiate this with respect to x, we're holding y constant, so it turns out to be just y, right? And that turned out to be f sub 1, okay? So yes, that makes sense there. And the constant here, think of that as like 2 or something. It's just a number, so when you differentiate once, it goes away already. So now let's do partial v, partial y. So now we're considering x a constant, so then we just get x. And again, the constant goes away, all right? So you could have a 2, a 4, a 3, it doesn't really matter. So the point here being, so this was f sub 1, and this is equal to f sub 2. Okay. Anyways, the point here is that anything like this, so xy plus 2, let's say, and v of xy equals xy plus 79. It doesn't matter what the constant is here. That's why it can differ by a constant. Okay, and this is our potential function that we're talking about, our v of xy, or v of xyz if you're working in 3 variables. But basically, this constant here doesn't really matter in the long run. Okay, so that does it for this section, and I'll talk to you in the homework video if you watch.
We just use for fun.